Okay, let me share my screen. Okay, do you see my screen?
Yes.
Very nice. Very nice. Okay, so I'm doing this education session because I participate in the Womanium Quantum program. So on the screen you can see actually the website for this program, and it is kind of very interesting, very good program because it gives like a lot of information about kind of different kind of topics on quantum computing, quantum sensing, quantum applications. There is lab tours and everything. So, and also if you can see, there is like a lot of speakers. There is like so many people from the quantum industry. There is like CEOs, different kind of engineering scientists, different leads, and kind of a lot of various people from the industry. So maybe you would like to join this program like next year, since they do it like everywhere, like every year. So some information about me, about the speaker. So I basically recently graduated as a doctor in business administration. I'm master in computer science and have 2 other university degrees. And also I have like I was working like 18 years in software engineering. I know more than 18 programming languages. And then I earned more than 200 certificates in various topics, like in business, in psychology, and in technology. So let's go to the lab tour. I want to show you the Quantum AI campus. It's a campus of Google, where they develop their quantum computers and they do their research. By the way, Daniel, I would like if if it would be something like a dialogue. So if you have like any questions, or there is like something that you like to tell me more about, like you like feel free to interrupt me and ask your question, or kind of okay. So sounds great.
Can you a little bit? I'm going for my glasses.
Okay, sure.
Now we can continue. Thanks.
Oh, super. Let's continue then. So it's a quantum AI lab, and they have a picture of quantum processor, quantum computer itself, and then let's go to the tour. So they kind of start with showing us the planet. And then we can just go to this campus in Santa Barbara, when they develop the quantum hardware, software, and quantum algorithms. So here it is. Here is their lab, and basically in this place, and then we can enter the building in which they build their quantum technologies. So this is how it looks inside. So at the center of this laboratory, you can see the quantum computer. This is basically this size. And there is a dilution refrigerator when they have very cold temperature. So to make a quantum computing possible, they get a temperature of almost absolute zero, like 10 millikelvins. It's like minus 273 degrees of Celsius. It's like super, super cold. But only this makes the quantum computing possible. So let's come closer. This is how it looks. So you can see it's like a dilution refrigerator, and this all the communications that comes to the quantum processor. Quantum processor is actually a very small device. It's a size less than a coin, and this is all just communication, and it just makes possible to send some signals to the quantum processor. So this are actually made of like partially it is made of gold. And then
sorry, how does that little thing smaller than a coin can make that that awesome things and process a lot of things?
That's a very good question because we talk about quantum technologies, and the quantum particle is very, very small. You know, those atoms contain the quantum particles, or like photons or ions. They are super small. So the actual particles are super small, and then we need only very small device in which we can contain those those super particles. So let's go. This is actually the quantum processor, so it may look big on your screen, but actually it's like super small device. And you can see like many cables can be connected here, so they have those connectors. And then if you look on this processor closer, it looks like this. So they say it's 150 square millimeters. So it's like very small thing. And then this is, if we look on the quantum processor with the microscope, we actually see the qubit. The qubit is actually quantum bit. So this is how it is implemented in hardware, and this is actually what makes the quantum computation possible. So this size is like just 10 micrometers squared. So it's like super small. And then let's see actually what is quantum computing. So how we make it possible to compute, or like using such a small particles. So maybe you heard about the double slot experiment when the physics sends the electrons through the slots. So slots are those holes in this barrier. And then kind of if they don't have an observer, then they kind of see the something like a wave on this screen. But if they have an observer, they have like a particle. So basically, if we send an electron through the hole, then the particle behaves like a wave if we don't observe it. But if we observe it, then it behaves like a particle. So kind of if we put some measurement device here, then we can find out then the electron, it kind of flows either through the left hole or through the right hole. But if we kind of don't try to understand it, then we have this kind of superposition, this wave. So maybe I don't know if you heard about it, but this is like very kind of very like experiments that everyone talks about. Like many people talk about this, and here is actually interesting interesting concept of Schrödinger cat. So Schrödinger was a scientist who actually worked with quantum physics, and then he came up with some hypothetic experiment in which they put a cat into some box, and then in that cat there is like some radioactive material, and there is a radioactive detector. And then the physics particles, they have such a characteristics, then they can measure the radioactive decay with some probability. So if we so at some moment the device is made this way that if the the detector measures the radioactive material, then it hits the some bottle with poison, and then cat gets dead. But if the detector doesn't measure the radioactive material, then this detector doesn't trigger the device, and the poison didn't get into the box, and cat stays alive. But at the same time, this kind of quantum particles, they have such a characteristic that there is like a 50% of probability that this radioactive material will be measured. So if we don't open the box, then we think that the cat can be dead and alive at the same time. So if we open the box, we can find that cat either dead or cat alive. So if we open the box and if we observe the cat inside, we only find it is dead or it is alive. But if we don't open the box, then the interpretation is that the cat is dead and alive at the same time. It's interesting concept of the quantum physics that a lot of people talk about. So, and we actually use this idea of quantum physics in the quantum computing. So maybe you know this, that all the information can be coded as zeros and ones. Like, for example, we have a Zoom meeting and we see each other and we talk, and our speech can be coded as zeros and ones. And also, like my my video can be coded as zeros and ones, and your zeros can be coded as zeros, and all the information, all the text here, like all kind of information can be zeros or ones. And so we are both green today, and then you can see the green screen like a matrix, and the picture tells that there is only 10 types of people in the world, those who understand binary and those who don't. And the 10 actually is not 10, but it's 2 if we read it in the binary code. Maybe you have questions so far?
No.
Okay.
I do everything.
Cool. Then let's go to the next next screen. So as I already told, all the information can be encoded in bits. So bits can be either 0 or 1, and this is in classical computers. In quantum computers, we have quantum bits, and quantum bits are much more interesting because it can be 0, it can be 1, and it can be something between 0 and 1. What does it mean? That it can be something like with 70% of probability 0, or like 70% probability 1 and 30% probability of 0. Basically, the qubit is some point on the sphere. As you can see, it's a sphere here. And if we put if we activate it in some position here, then if you see, it's closer to 1, 1 is on top, and 0 is on bottom. So if we measure it in some time, then it have more probability that it will get to the position of 1, and less probability then it will be 0. It actually something like our planet and equator. So if we take a look on the Google Maps, we can see we live on the planet, and the planet is like a sphere. And this is like a qubit. Let's say that the one would be on the North Pole on top here, and the 0 would be on the bottom pole, on the South Pole on bottom. And then kind of, for example, you are somewhere in Mexico City, kind of somewhere here, and this would be kind of your position on the sphere. So it will be your value of kind of your qubit, let's say. And then we can see that you are closer to the North Pole, so you are closer to the 0, and you are further from the South Pole. Then kind of if we measure you, then there will be kind of probability that you become like a 0 in this case. If you would be on the equator, or if I would be on the equator and we kind of measure, then it will be the same chance that it will be 0 or 1. So we kind of use this kind of qubits to make the computations. So instead of encoding all the information like here in 0s and 1s, we could also encode all the information in the qubits in some probabilities of 0s and 1s. And this gives us more opportunities because quantum computers are much more performant. So they kind of, if some tasks that we compute on classical computers needed to kind of years, or maybe kind of tens of years, or maybe centuries, or maybe even thousands of years, then quantum computers would solve the same tasks just in seconds. So they are kind of much more performant because they can compute the same things, but much faster. So you are kind of interested in music, and then I would like to show you something. Actually, I contacted this professor, and he is the creator of the quantum music. So what he did is that he used those qubits to make the music. So you kind of play piano. So you may be kind of interested in this project because they made the music possible, but not with classical beats, but with quantum beats, with those qubits. And then they kind of have an interesting device. So that kind of here. Let's see. So basically, they change the value of that qubit, and then they get quantum music.
That we're at
In different ways.
tonight's event is kind of special art and culture.
Like, look, he has a device on his finger here. Like if you see his finger, he has some device that he wear on his finger, and then when he rotate his hand, he is able to change the value of that
The way
qubits.
Fink had talked about emerging technologies such as quantum computing.
And then because he rotate his fingers, then he change the value of qubit, and then he creates those kind of quantum sounds.
I see this relationship as a collaboration. So
So he actually created very interesting music project. And that music project, he called it like Ludovico Quanthoven. It's like similar like Beethoven. So let's take a look. Do you hear the music?
Ludwig van Beethoven, Ludovico Quanthoven.
Ludovico Quanthoven. Yeah, it's like a Beethoven, but Quanthoven. Do you hear the music if I play it?
Yes. No, I don't listen it anymore.
You didn't hear?
No.
And now?
No.
No? I could just send you the link to this project, so
Okay.
you could listen it later. But what is cool about it is that they basically created a kind of artificial intelligence made on quantum computing that kind of learns the classical music, and then it is able to generate the same classical music. So what is it? Music is not created by a human, but it is created by a quantum computer artificial intelligence. So it's kind of very new field, and it's kind of super cool. So let's go next. So here I would like to show you some kind of simple quantum programs. This is very simple program, and this is basically an algorithm that gives us a random bit. So basically we can get 0 or 1 with the same probability. So we start like we have a kind of initialized qubit in the and we get it in the value of kind of 0. And then we have a Hadamard gate. Basically, the Hadamard gate, it moves our qubit to this position on the equator. So let's say the Hadamard gate would move the would activate our position on the equator. So it has the same chance of probability of be measured like a 0 or 1. And then we kind of measured this qubit, and then we kind of every time we run this program, we can get kind of either 0 or 1. You see, before we have 0, now we have 1 here. We run it again, we get 0. We run again, 0 again, run. Now we get 1, so it will always have 50% chance of getting 1 or 0. So you see, it's like a very simple computer quantum computing algorithm, kind of the most simple possible, I think. And it has just 4 lines here. So basically, we allocate 1 qubit here. Oops, move it out of here. Then we kind of initialize it as 0, and then we apply it Hadamard gate in position of that moves the qubit in the superposition between kind of 0 and 1, and then we kind of measure the result. So when we measure result, our value of qubit will become either 0 or 1. And it is similar, like you remember, I told you about this experiment. If we kind of have an observer here, if we have a measurement device, then our electron will fly either through the left hole, either through the live hole. So this is what we get when we measure it. But before we measure it, it's kind of in superposition between 0 and 1, and it actually kind of flies through the both holes. So kind of the same kind. So before we measure it, the CAD is kind of dead and alive at the same time. So the kind of cat is dead with 50% chance and alive with 50% chance. But when we measure it, we will find the cat alive, or we will find the cat is dead. So when we open the box, then we see in what state the cat is.
Yes, I have a question.
Yes.
A question.
Mm-hmm.
Wait, I forgot.
Sometimes.
Yes. Can you get 0 and 1 at the same time or no?
If you measure, you will get only 0 or only 1. You cannot you cannot measure and get both. So you will have either 0 or 1. But before you measure, you will have 0 and 1 at the same time. It would be like something between 0 and 1. So before you measure, like, look, what is here, the last thing here, it's maybe very small. I don't know if I can make it larger. Yeah, look, I can make the circuit larger. So this is kind of measurement device, this kind of half of a circle. So this measurement device actually measures the kind of in what state the qubit is. So this device will give us either 0 or 1. But before this measurement, this qubit is kind of in superposition between 0 and 1. So before we measure it, it can be 0 and 1 at the same time. Did I answer your question?
Yes, thank you.
Cool. Well, the same way we can actually make the quantum byte. So bit is like byte is 8 bits, and quantum byte would be kind of 8 quantum bits. So you see we have kind of 8 qubits here, 1, 2, 3, 4, 5, 6, 7, 8. And then we put each of those qubits in that superposition with the Hadamard gate. And then we measure them, and then at the end we get some kind of some random value of the qubit. So here it says like 0, 1, 0, 1, 0, 1, 0, 1. Let's run again. We get many zeros and just 1. Let's run again. We get also like 2 ones and many zeros. So it's basically some kind of random byte. There are kind of many algorithms here, like a swap test. So the quantum circuits would look like this. It's just kind of, I would like to show you some examples of how the quantum programming. Basically, we can write this code, and then we can have this circuit. This is what we program with this code, but represented in the graphical kind of graphical view. So there could be kind of different quantum algorithms. So it's all various quantum algorithms. So you can see some circuits are small, but some could be kind of very big. There is even quantum algorithm to, for example, like as we already say, there is a quantum algorithm to create music. There is a quantum algorithm to kind of find the shortest path. For example, if you want to travel and if you kind of have if you want to visit 20 cities, there is a quantum algorithm that can find you the shortest path so that you would spend less money and you would kind of visit all the cities. So it's kind of very difficult problem in computer science. And then quantum algorithm is the best kind of that can solve this problem in the shortest time. There is some quantum algorithms for analyzing financial markets, for for logistics. There is quantum algorithms for creating new materials or for kind of drug discovery. So there is kind of many applications already possible. So now I would like to show you how looks some more complex quantum algorithm. So this algorithm actually does a quantum teleportation. The quantum teleportation is kind of allows you to send information between two qubits. Basically, we kind of entangle those qubits. Like when the qubits entangle, they are kind of synchronized between each other. Then if we have like one qubit, like for example, we could meet and we could synchronize our qubits, so they would have a kind of the same state. Then, for example, you will stay in Mexico City and I go to Cancun, and because we entangled our qubits, if you kind of change value of your qubits, then value of my qubit will also change. So basically, the quantum teleportation allow us to teleport information on kind of on the distance. So it's kind of interesting characteristic of the quantum technologies that classical technologies do not have. And also quantum communication is much more secure because like, for example, if we use a kind of classical computer and someone would like to listen kind of our Zoom call, then we don't know if someone listen or not. Like, for example, some hacker join and he can just listen us and we don't know about it anything. But if we would have a kind of quantum communication, if we would have like a quantum Zoom, yeah, it is not built yet, but we are kind of getting to that. So in the quantum communication, if some kind of hacker would like to listen us, then we would certainly know about it, and we will say that somebody listen us. So let's kind of try to use other communication channels. So the quantum technologies, quantum communication can be much more secure. And here is even more complex algorithms. This is like a quantum Fourier transformation. This is used in also kind of this algorithm could be used in music. This can be used in kind of in encoding or decoding information, like in cryptography, in some kind of compressing the information thing. So this is basically very interesting. We have like a quantum byte here, or kind of 8 quantum bits, and then you can see we kind of can swap various bits. We have a kind of H gate, S gate, and Z gate, and you see it's kind of this way we have a quantum computation. And because we kind of change values of those qubits in the beginning, then we can see that those qubits, kind of values of those qubits also change. And you can see that kind of the rotation goes with various frequencies. It's basically the algorithm that allows us to kind of switch our basis of computation to 4 frequencies. I studied in the MIT quantum computing programs, and one of those professors, so there was like Will Oliver, Isaac Chuang, Peter Shor, they all kind of very important people in the quantum computing industry. And I want to highlight Peter Shor because he created an kind of algorithm that kind of Shor's algorithm. The algorithm is called with his name, and these algorithms allow us to decode any information in the world. Like if you can see, kind of in every browser we have like an encryption, and basically he created a quantum algorithm that allows us to kind of to decode any information in the world, even if we don't know kind of the even if we don't know the cipher, if we don't know the key, how to decode it. So
Everything, like
yeah,
everything.
yeah, absolutely everything. You can just decode any information in the world. And because the information is like a new oil, it is kind of super expensive, and many businesses are made just on information, like a Facebook business or kind of businesses businesses, so kind of Google and kind of many big companies. This basically allows us to get any information in the world, and the person who will create a sufficiently powerful quantum computer first, he will become super rich because he will able to get all the world information. But now we are still years from it, because here is like a roadmap of the IBM, and IBM created actually the most powerful quantum computer at this moment, and it has just 433 qubits. So you can see they have created Osprey processor. It has 433 qubits. 400 qubits is not enough to kind of to run the short algorithm and get all the information in the world. But you see the kind of in 2026 or further, they have a plan to scale their quantum processor to have like 10,000 qubits or even 100,000 of qubits. And at this point, getting all the world information will be possible.
Yes, but that's very dangerous, right?
Right.
If it gets into the wrong hands.
Right. It is, and this is the reason why so many countries invest kind of billions of dollars in the quantum computing. Is just because kind of countries compete who first can create the quantum computer, and like whose country's secret services will get all the world information. So the kind of China invested like I think like 10 or 15 billions of dollars in quantum computing. The US invested like a little bit more than $1 billion. So I don't know if Mexico invested anything. Let's see. Quantum computing efforts.
And Russia, has Russia invested in computer?
Good question. The Russia invested. So here is the diagram. Russia invested $633 million. Kind of not much, but already kind of already good to start with the quantum computing technology. So China, 15 billions invested. United States and Canada, they invested a little bit more than 1 billion. We see Mexico didn't invest yet, but maybe we check another how much Mexico invested in quantum computing. Actually, look, Northern Mexico. Actually, Northern Mexico. I guess Northern Mexico is just the north of Mexico. If my assumption is right, then Mexico City Taiwan-based electronic manufacturer Quanta Computer will invest 1 billion in the northern Mexican state of Nuevo León. So actually, Mexico also get a kind of very huge investment in the quantum computing industry.
Yes.
And so there is like huge opportunities. And here I would like to show you the diagram. It's basically what people are needed in the quantum industry. And you can see one of the most needed people in the quantum industry is a person who can develop quantum algorithms. So it's basically the quantum algorithm is what I showed you here. And here, so basically need to write a code and get some tasks done, some computations done. So and then also kind of many physicists, scientists, engineers, chemists, and marketers, developers, architects needed also in the quantum computing industry. Also, another cool thing that I would like to show you is this kind of desktop quantum computer. It's already kind of the first quantum computer appeared. It kind of cost kind of expensive, $5,000, but like there is surely people that find it kind of affordable for them. And this is just kind of very beginning. We kind of surely know that soon will appear more powerful quantum computers, kind of personal quantum computers, and with less cost. So this quantum computer is the super simple. It has only 2 qubits, kind of those qubits. Like in this algorithm, we have 8 qubits. In this algorithm, we have like just 1 qubit. So for some algorithms, it would be enough to have this personal quantum computer. But this is just kind of interesting example, but mostly how people use a quantum computer. They are just going to something like Amazon Braket or IBM kind of quantum, IBM quantum cloud. So you can see that they have the same kind of circuit design, and it is possible to write a quantum computer code. It is either in Open Quantum Assembler or in Qiskit. So there is like several libraries for writing a quantum computing code. And then basically there is other kind of cloud services that allows to do quantum computing, because kind of quantum computers are super expensive to build and maintain. Those cloud providers allow us to just connect and kind of do quantum computation for kind of very limited amount of time, so that we don't need to buy the quantum computer, or we don't need to build it. And we can just connect, and we can use quantum in the cloud, so we can run kind of any algorithms that we could have. Also, here is another kind of library. It's a Cirq. It's from Google. And then kind of there is like various providers, kind of actually many providers available that allows us to have those kind of quantum computations. So such a company like Quantinuum, actually, they created very interesting technologies, because there is like various quantum computer hardware and also various computer software, and there is kind of different languages appear. So kind of in this website, we can see that any kind of quantum algorithm can be written in 5 languages or libraries. So QC engine, Qiskit, or Open Quantum Assembler, or QSharp, or Cirq. So those 5 technologies. So this company kind of created a super cool thing. They allow us to write code on their with their library, and then allow to convert this code to any other programming language or a library for quantum. And basically, they also allow us to run that code on any kind of quantum hardware. So here kind of we see how the financial kind of industry professionals use the quantum technologies. They basically can analyze the stock market prices with quantum technologies, and then can use quantum machine learning to predict the future prices. And then this is basically, I think that's it. So maybe you have any questions about the kind of quantum technologies, or kind of any about quantum algorithms, or kind of anything that we discussed?
No, No, so it can the let me see that if I understood.
Sure.
So quantum computers work to make predicts about like financial things
Mhm. Right.
and solve complex problems in math.
Right. Correct. So the first what computers can do, that they can analyze the stock prices. So like if we take a look, like for example, Bitcoin price. So we can see this kind of this price of the Bitcoin for just one day, but we can take a look for kind of 1 year price or maybe even 5 years. So we can get this data from the stock market, and then we can kind of put this data to the quantum machine learning algorithm, so that algorithm will analyze this data, and then this quantum machine learning would be able to predict the future prices so of Bitcoin. Like what, for example, what would be like the price of Bitcoin tomorrow or maybe after tomorrow. Sometimes it's good to know what will be the price, because we can make a kind of decision if we should buy more of that Bitcoin or maybe we should sell more of that Bitcoin. So this is one thing what the quantum computers can do. The other thing what can quantum computers can help is that they help to create a financial portfolios. Like for example, you could have like Bitcoins, you could have Mexican pesos, you could have like US dollars in your wallet, and maybe you would have some kind of stocks of companies. I don't know, like stocks of Google or maybe some quantum companies or stocks of Apple, like stocks actually of any companies. So the quantum computers could tell you how much of any kind of stocks you can have to build an optimal portfolio that is kind of less risky, but also can bring you more value. So that kind of you need to spend less money, but at the same you will kind of get more value with your portfolio. Does it make sense?
Yes, it makes sense.
Cool, very cool. All right. Any other questions?
No, at the moment, no.
Okay. Then I think we finished with the lecture. Now, kind of, I would like to ask you, like, how was this kind of your experience? Maybe what did you learn? Kind of, did you have any insights? And kind of, what do you think about all this that I tell you today about?
I think it was very interesting. I think I learned how it looks a quantum computer,
Uh-huh.
that the quantum computer processor it's very small,
Uh-huh.
that um that it yeah, that it looks like 50-50
Uh-huh.
with the Schrodinger's cat.
Uh-huh.
We can make music with quantum computers,
Uh-huh.
that quantum computers don't use the usual 1 and 0.
Uh-huh.
It uses the well, like probabilities
Mm-hmm.
between 1 and 0.
Mm-hmm.
Um, Also, that in few years, maybe we can get all the information in the world
Mm-hmm.
by the codification,
Mm-hmm.
but there is not a quantum computer that has the ability because it requires a lot of
Mhm.
qubits,
Right.
and that it works to solve very complex mathematical problems and predict like financial things.
Mhm.
Yes.
Okay. That's very, very cool. Kind of you learned a lot today. So thank you, Daniel, for kind of attending this session and for your time and for your attention. So if you would have any questions like about quantum technologies kind of later, feel free to contact me at any time in ask something about it.
Thank you.
Okay, sounds good. Well, I think we are done. So, and we kind of it was nice to talking to you today, and kind of have a great day.
Yeah, thank you. You too. Have a great day. Thank
Okay,
you.
thank you,
Thank
Daniel.
you. Talk. Thank you for your time of explaining the quantum basics.
Mhm.
Yeah, thank you.
Thanks.
Have a
Bye.
great day. Bye.
Thank
Bye.
you. Bye bye. Greetings to everyone.
Thank you, you too. Bye.
Bye bye.